You know, the AI boom, it feels like magic, doesn't it? You get instant answers, you can create incredible art, it all just sort of happens in the cloud. But here's the thing, the cloud is a very real physical place. And right now, it is getting seriously hot. We're going to dive into the invisible crisis that's threatening to slow down the AI revolution, its own massive heat problem.
Just think about this for a second. Every single time you ask a chatbot a question or get AI to generate an image for you, you're spinning up incredibly powerful processors in a data center somewhere on the planet. And all that work, it generates heat. A lot of heat. And that simple physical reality is fast becoming one of the biggest roadblocks for the entire AI industry.
So just how big of a roadblock are we talking about? Well, get this. In a lot of data centers, the cooling systems, just the AC basically, can eat up a mind-blowing 40% of the building's total electricity. I mean, can you imagine if nearly half your power bill was just for air conditioning? That's exactly why heat is now the #1 operational challenge they're all scrambling to solve. And this is what the industry is calling the AI heat wave. See, as AI models get smarter and more powerful, the chips that run them just get hotter and hotter. So hot, in fact, that the data centers we've been building for decades, they just can't keep up. We're not just pushing the limits of software anymore. We're hitting the hard physical limits of our hardware.
So where is all this heat actually coming from? Well, it's coming from things that look just like this. The newest AI chips can have a thermal design power, which is pretty much just a rating of their heat output, of over 800 watts each. To put that in perspective, that's like having a small microwave oven running at full blast inside your computer. Now imagine stacking dozens of those into a single server rack. The heat density becomes, well, it becomes almost unmanageable. For years, the answer to this problem was pretty simple, brute force. Just blast everything with massive amounts of freezing cold air. Think of these giant Arctic-level cold warehouses. But that whole strategy, it's officially hit a wall. It's way too expensive, it's inefficient, and when it comes to today's AI hardware, it's just not powerful enough anymore. So, what are we talking about here? Well, for starters, traditional air cooling really starts to struggle once a single server rack starts pulling more than 20 kilowatts of power. It uses a crazy amount of energy and water, and the fans are so powerful they are deafeningly loud. But the real deal breaker, the absolute showstopper, is that last point. With the kind of super dense hardware that powers modern AI, air simply can't move the heat away fast enough. The chips would literally cook themselves to death.
Okay, so the industry has a way of measuring this. It's a metric called PUE, which stands for Power Usage Effectiveness. It's actually a pretty simple ratio. You just take the total power the facility uses and divide it by the power that the computers actually use. A perfect score is 1.0. Anything higher than 1 means you're wasting energy on overhead. And a huge chunk of that is cooling. For data center operators, the name of the game is getting that PUE number as close to 1.0 as humanly possible. So, if air cooling is hitting its limit, what's next? This is where things get really interesting. We're seeing a fundamental shift in the whole infrastructure. The liquid cooling revolution. And this isn't just a simple upgrade. It's a complete rethinking of how we manage heat at a massive scale. And honestly, it's becoming absolutely essential to unlock the future of AI. And the difference between air and liquid is just staggering. I mean, on a molecular level, water can be up to 3,000 times more effective at transferring heat than air. It's not even a fair fight. Where air chokes on a 20 kilowatt rack, liquid can cruise past 100 kilowatts without breaking a sweat. And what's the result? You get massive energy savings and the ability to cram way more computing power into a much smaller space. It's a total game changer.
And there are a few different ways to get this done. Over on the left, you're looking at what's called direct-to-chip cooling. This is where liquid is piped right onto the hottest parts, like the CPUs and GPUs, to pull heat away right at the source. And on the right, that's a rear door heat exchanger. It basically replaces the back door of the server rack with a big liquid-filled radiator that cools the hot air as it flows out. And then for the most extreme, power-hungry applications, there's full immersion cooling. And yes, it is exactly what it sounds like. Entire servers are literally dunked into a specialized fluid that's amazing at conducting heat but doesn't conduct electricity. It's the most efficient method out there, really designed for the absolute peak of high-density computing. Okay, so if liquid cooling is so obviously superior, you might be wondering, why hasn't everyone switched over already? Well,
Because it is a massive undertaking. We're not talking about just swapping out a fan here. This is a fundamental, incredibly expensive, and really complex transformation of a building's entire infrastructure.
To put a real number on it, one industry expert just put it bluntly. He said, it's very expensive, like $5 million per megawatt just to equip it. Let that sink in. $5 million per megawatt. That's a multi-million-dollar investment for the cooling system alone before you even start buying the actual servers.
And this picture right here shows you why it's so expensive. You are essentially adding an entire industrial plumbing system on top of a high-tech electronics facility. You've got overhead pipes, super powerful pumps, these complex things called coolant distribution units. I mean, it is a massive mechanical and electrical overhaul from the ground up.
So what does an overhaul like this actually look like? Well, it's this really meticulous 5-stage process. You have to start with a deep dive site audit and a super complex system design. Then you've got to completely restructure the power grid, rip out the old racks, and install new ones. And then, finally, integrate and test the whole shebang. Every single one of these steps requires an incredible amount of coordination.
And how long does this all take? From the first day of planning to a fully operational system, you could easily be looking at a timeline of up to a year. This is not a quick fix. This is a long-term strategic investment that data center operators need to be planning for, like yesterday. But here's the twist. Solving the heat problem, well, it introduces another major environmental headache. Because even though liquid cooling can be way more energy efficient, all that heat it pulls away has to go somewhere. And very often, that process involves another incredibly precious resource, water. And yep, you guessed it. Just like PU for power, the industry has a metric called WUE, or water usage effectiveness. It's the same idea, a ratio of how much water a data center is using for things like cooling compared to the energy its computers are consuming. And just like PUE, a lower number is always better. It means you're being more efficient with your water. See, even with these really advanced liquid cooling systems, that captured heat has to be rejected from the building. And how do they often do that? With these huge evaporative cooling towers. These things basically work by evaporating millions and millions of gallons of water into the atmosphere. It creates a massive water footprint, which is a really serious problem, especially in parts of the world that are already facing water shortages. And that really leaves us with the central dilemma of the entire AI age, doesn't it? We're building this unbelievable digital future, but its foundation is very physical, very power-hungry, and very thirsty. So the big question is, how do we balance our relentless drive for digital progress with the very finite resources of our actual planet? Figuring that out isn't just an engineering challenge, it's one of the biggest tests of our time.